Hello. So today we are indeed talking about wave speed and interference. If you're looking at this sign and feeling like it doesn't quite look like my handwriting or looks a little weird, you'd be right. So if you haven't been able to notice already, the camera actually flipped things around, and I wanted to write this on the whiteboard like this. So this is actually written backwards. I didn't write it right. See how the expo is written the other way? I wrote this backwards so that it looks right on the camera. Wow. Weird things aside, hello. Coming to you today in my high school hockey jersey because I'm running out of things to wear in my house. But we are going to actually begin what we're talking about today, which is wave speed interference. So our first two topics are last time we talked about two different forms that waves come in, which would be transverse and longitudinal. But there's actually two other types of waves. Like there's two forms that they come in and two types that they come in, which just sounds weird. But I'll explain what I mean by types. So the two types are mechanical and electromagnetic. So mechanical waves are waves that require a medium to travel. And what's a medium? A medium is like the means of travel, the substance that the wave is traveling in. So mechanical waves need a medium. They need a substance to travel in. It's like sound. Sound travels through air molecules, right? If we were in space and someone yelled, you couldn't hear them because there's no air to travel or for the sound to travel through. So sound is a mechanical wave because it needs a medium. Electromagnetic waves are waves that can travel without a medium, like light waves. Light waves travel to us from the sun. There's nothing to carry the waves through space, right? They just travel right on through. They're electromagnetic, so they don't need a medium. Now, electromagnetic waves are we're not really going to look at, so everything we're looking at from here on out is a mechanical wave, meaning it requires a medium. And we'll talk a little bit more about that as we move forward with the first topic, which is speed of a wave. So mechanical waves travel through mediums at a certain speed. You've heard of the speed of sound before. Yes, so sound travels at some sort of speed. That's what the speed of sound is. So we'll talk a little bit more about that. So the speed of sound, or the speed of a wave rather, there's a formula for it. And here's the formula. So speed, wave speed is like before, is just a lowercase v for speed. The speed of a wave, and that's equal to two things multiplied together. The first one, I didn't talk about it when we talked about wavelength, but wavelength actually has a variable. And what wavelength is, the variable, so it's weird, it's a Greek letter. It's the Greek letter lambda, which looks like this. It looks like an upside down Y or a TP looking thing. So lambda, the Greek letter for L, sort of, for length, wavelength, right? So that's what wavelength right here, lambda. And it's lambda times script EF, which we've seen this before, frequency, right? And that's all. Speed, wave speed, is equal to its wavelength times the frequency that it's moving at. And that's how you calculate speed. Pretty straightforward formula. Just remembering that the lambda here, the upside down Y, is length, wavelength, right? Wavelength. And then the script EF is frequency. So we can use that in our next, actually I'll leave it. We can use that in our first question. Pretty straightforward question that it asks. The first question just says, a wave has a frequency of 15 hertz and a wavelength of 3 meters. What is its speed? So all we have to do is calculate that, right? So it says a frequency of 15 hertz. Script EF is 15 hertz. And has a wavelength of 3 meters. 3 meters. So our speed equals lambda times frequency, 3 meters times 15 hertz. Speed is 45 meters per second. It's meters per second, remember? We've got meters, 3 meters. Hertz is 1 over seconds, right? Remember, so 3 times 1 over seconds is, or meters times 1 over seconds is meters per second. So that's what we're getting for speed, meters per second. That's our speed of a wave. Pretty straightforward use of the formula. Obviously, there are not going to be many questions that are just this, because that'd be pretty straightforward, right? So I will erase. All right. That brings us to our second question. So that was just a very basic usage of the formula before I wanted to get to talking about more of like speed of a wave in particular. So the speed of a mechanical wave actually depends on the medium that it travels through. I don't know if you've ever, well, here, an experiment you can do at home. So find a wall or a table around you, and what I want you to do is I want you to stay off the wall first. I've got a wall right here, and knock on the wall and listen to the sound. Okay? Now I want you to take your ear and press it up against the wall and then hit it. Should be louder, right? So you're still hitting the wall with the same part of your hand. You're still, so it's still making the same sort of sound, but you're listening to it in different ways, right? So whenever you're off the wall and you're tapping it, the sound is traveling through the air to your ear, but when your ear's against the wall, it's traveling through the hard surface of the wall, right? And it was louder when you were doing that. So sound actually travels different speeds through different phases of matter. And let's look at why. So our second question here says sound travels through different mediums at different speeds. Rank the mediums in order from slowest speed to fastest speed, and we've got solid, liquid, and gas. So we did our little preview experiment, but I'm going to draw some pictures here to get us an idea of like why this is going on. So I'm going to draw like particles of these three different mediums, right? So it says solid first. Solid is right here. Solids have their molecules packed really tightly together, right? So it looks like this. Next we have a liquid. Liquid, particles can move more freely, right? They're slightly more spaced out from solid. And then we have gas. And gas is really spread out, right? Looks a bit like that. So, which one does sound travel faster through? Well, we can think to our experiment, right? Where when you hit your hand off the wall, whenever you were off the wall, it was quieter. And when you were next to the wall, it was louder. So if it was louder, right, we learned how that sound waves are longitudinal waves. So there was the simulation the other day, right, where you could see the particles bumping into each other and moving out, right? So as sound is traveling, it's particles bumping into the next one and transferring their energy, right? Because waves transfer energy. And so the gas is quieter than the solid because the waves are losing more energy in the gas, right? You're losing more energy, so it's not as loud when the sound actually reaches your ear. So since we can look at the solid here where all these particles are packed together, right? Since the particles are so close to each other, they have an easier time bumping into one another than we do especially in the gas, right? Because the particles are very spread out. So the sound actually travels faster in a solid because there's more particles that have an easier time bumping into each other than it does the gas. So it ranks pretty intuitively from there, right? Where we have, we're going from fast or from slowest to fast. So the slowest would be gas because these particles are very spread apart. So the molecules don't bump into each other very well. And then our middle would be liquid. And then our fastest would be solid. Solid being the fastest because there's more particles closer together, so they have an easier time bumping into one another. So yeah, and that's why that works. That's why it's louder whenever your ear is up against the wall. So yeah, very neat. Lovely. So that brings us to our third one, which is sort of just an application. I wanted to walk through an application of all of the steps we've looked at so far with analyzing waves. So I've got a little multi-part problem here with a couple of graphs. But here's what the problem says. It's got two graphs. One that has vertical versus horizontal position, and one that has vertical versus time. And the problem says, a group of students conduct an experiment in which a 2-kilogram block is secured on top of a vertical pole that has a spring around the pole. Basically, it's describing like an oscillator. There's a machine making the string oscillate like in the simulation that we looked at in the previous lesson. One end of a light horizontal string of unknown length is attached to the block, and the other is secured to a wall. So it's connected to a wall. The oscillator is making waves in the string, basically. This is just a big setup, really. And then it says that you've got the graphs that were given that I talked to already. So really, the problem was just to set up to tell you what's going on It's an experiment setup where some students are using an oscillator. So our first question is what is the frequency of the wave? And we're trying to figure out what, so frequency, remember, is oscillations per time. It's waves per time, if you will. So what we need to do is figure out how many waves there are per what amount of time. So if we look at the graph here, right, it starts on a high point, and then it goes down, and then it goes back up. So it looks like this is easier. Remember, whenever I told you previously when we were looking at graphs, it's usually easier to figure out the period from a graph. So it makes one complete oscillation over those 0.2 seconds, right? 0.2, we have, that's our period, 0.2 seconds, because make one oscillation over the 0.2 seconds. So our period is 0.2 seconds. And we can figure out the frequency, right? Because frequency is just inverse period. So 0.2 goes on the bottom here, and you just flip it. So 0.2 flipped is 5 hertz. That's our frequency. Easy peasy for part A. Just found the period from the graph. We used the time graph, right? Because we were looking for the per time, right? We weren't worried about the horizontal vertical position on this one. All right. So B says, what is the wavelength of the wave? So we're looking for the length of one wave. And to get the length of the wave, I need you to turn your attention to the graph on the left, right? Because the graph on the left has the horizontal lengths here. If you were looking for the wavelength on the time graph, you would just get like a length of time, which that's not a wavelength, right? Wavelength is like a measurement, like meters measurement. So we need to look at the graph on the left, which has the horizontal position on the x-axis down there. So we're looking for wavelength, which means we need to either measure crest to crest, trough to trough. Those are the easy ones, remember, or skipping a step to measure the middle points. But it looks to me like since we start off on a trough, that should be our starting point. So we'll measure, we're at 0 and we're at trough. Our next trough happens at 4 meters. So pretty straightforward, right? We go from trough to trough. That's our wavelength. One complete oscillation is 4 meters for part B. Lambda equals 4 meters. Right? Wavelength of the wave. Lovely. C says, what is the amplitude of the wave? So we're just looking for the height of the wave, right? Rest to crest is how I said it the other day. And we can use the graph on the left here again. Rest to crest, the rest position here is at 0. It's at the middle position, and it looks like the peak from 0 is 0.2, right? So 0.2 clearly is our amplitude. C, amplitude sort of has a variable. It's a capital A, but not really. Not a super strict variable. 0.2 meters, generally. Lovely. All right. And then we have D. D says, what is the speed of the wave? Well, we learned how to do this, right? On the previous page, we saw that speed is equal to wavelength times frequency, right? So we calculated our wavelength earlier, 4 meters. And our frequency in the first question is 5 hertz. 5 times 4 is 20 meters per second. That's our speed. Easy peasy. Waves aren't hard, right? You can do this. Flip on over. That's really the completion of our next topic, because wave speed is pretty straightforward. Travels faster through solids than gas, and speed equals wavelength times frequency. You guys can handle that. Great. So our next topic is interference, which is our next big jumping off point for the next part of the unit. Interference is very key to what we're going to be doing next. And interference is just when two waves collide, something happens. And there's 2 types of somethings that we'll talk about. So there's constructive interference and destructive interference. This will be very intuitive sounding whenever I tell you that constructive interference is when 2 waves collide and they build off of one another. So if you watch the simulation right here, this is showing you an example of constructive interference. Notice how both of the waves are on the same side of our string here, right? And you can see that as they come together and collide, that the new wave that they're forming is taller than both of the original waves, right? They're building together. So this one is taller than either of the two waves were combined. Interesting. So constructive interference is when two waves collide and they build on one another. The next one is destructive interference. So turn your example, we'll probably guess what destructive interference is, right? It's when two waves collide, but they're canceling each other out effectively. They're destroying, destructive interference, destroying one another. So take a look at this simulation where we've got one wave is on top of the string and the other one is on the bottom. So this time when you're running them, they collide, and instead of building, right, they're canceling each other out. You can see it's you have to look closely, like at a point that when the waves are right over top of each other, they're canceling each other out, and you can see the string is flat because they're destroying each other, right? They're going away. So it's a destructive interference. Makes sense, right? Yeah, that's kind of the basis of it. It's not, those concepts aren't too complicated. This really isn't a very complicated concept. I think you guys can handle this. But we've got a couple of problems just to like draw out and see our understanding. So number 4 has a little wave, 2 little wave pulses. A pulse is just like a single wave motion, a single hoop thing. 2 waves move towards one another as shown. In the quest, we've got a little picture. There's 2. They're on the same side of the string here. So what kind of interference are we going to get? Constructive, yes. And we're supposed to draw the resulting wave at the moment they're right on top of each other. At the moment they're overlapping. So I'm going to actually pull in the sheet here, I think, just so I can use the grid. So I've got these 2 pictures. We've got the 2 waves here, and they are moving towards one another. So if you take a look at the top part where we've got the 2 wave pulses, so each of these wave pulses right here are 2 units tall, right? The base is down here, and they're both 2 units tall. And so we're looking at when they're right on top of each other, right? So I'll draw them here in the middle. It's kind of dashy. Like when they're both right on top of each other right here in the middle. And constructive interference is saying they literally just add on top of one another. So if we've got 2 waves of 2 units tall and they are on top of each other, it's basically like you're just literally stacking them on top of one another. So the middle point, we've got two unit tall waves, so we're going to get a 4 unit tall wave. So if this is my rest here, the peak of the wave right here in the middle is going to be 4 units high. All right? And then it's basically just the same shape as if they were added on top of one another. So it'll roughly look like this. We're going to see how the shapes work a little bit more in a different problem. But yeah, we have 2 unit tall waves. They come together and make 1 4 unit tall wave. Pretty easy, right? They just add on top of one another. Really straightforward. That brings us to number 5. So to give you a little bit more of a visual on what these or how the shapes really add on top of each other, we've got wave pulses of different shapes. It's not really easy to make a shape that's not a wave, like a hump, right? But this is just for like illustrative purposes. So again, we've got 2 waves that are moving towards one another on each other on a string as shown below. And we've got a square wave here, a square wave pulse, and a rounded wave pulse. And the problem this time, they've got speeds, right? Each of them has a 1 unit per second speed. And the problem says draw the resulting position of the string 4 seconds after the position shown above. So they're both traveling at 1 unit per second towards one another, and we're drawing the position 4 seconds after what was shown above. So each of them is going to travel, right? If they're going 1 unit per second, each of them is going to travel 4 units, right? So we'll start here on the left one. 4 units later, it's 1, 2, 3, 4 right here. 4 units later, this one is 1, 2, 3, 4 right here, right? They're right on top of each other. So it's basically the same situation as the one before. They're right on top of one another. And they're on the same side of the string, right? So we're getting constructive interference, right? They'll be adding to each other. And like I said in the previous one, although it was harder to see, it'll be easier to see with this one, is you're literally just adding on whatever one wave to another wave. You're just adding them on. So if we take, I'll leave the square wave here as our base, and we'll just take the 1 unit tall hump of a wave, and it's literally just going to be adding on top of this wave. So I can literally draw it right up here like this, right? Because we'll add this extra height right here, up here. I'm just sticking this shape on top of this shape, right? And that's our resulting wave. So if we're drawing it down here in the box, on the bottom, we draw here, meet in the middle, and it looks like this. Square, with a little house, hump on top of it. Boom. Right? They're adding together. You're adding the hump on top of the square. That's all that's going on here. All right. Last but not least, we have number 6. It says 2 wave pulses are moving towards one another. The centers of the pulses are located at point X and Y. Draw the resulting wave when the centers of the 2 pulses overlap. So just when they're right on top of each other once again. Okay. So we've got our 2 unit tall square wave here, and another 2 unit tall just hump wave that's on the opposite side of the string though this time, right? It's on the other side. So what we're going to get here is destructive interference, right? And we're drawing them when they overlap. So they'll hit the middle, and the shapes will look like this, right? We've got the square on top, and then we've got the hump on the bottom. Lovely. So that means that they're destructively interfering. So this wave down here on the bottom is effectively taking away from the wave on top, right? We're subtracting this shape here from the square. So here's what's going to happen, right? We'll start at the middle point. The middle point of the hump wave is 2 units tall. The square wave is 2 units tall. So if we're subtracting this 2 units shape here from the middle, right, we're going to have 0 right in the middle shape on that X and Y point right in the middle. It's going to be 0 because we had 2 and we took away 2. And then you're subtracting away this little bit until you get to the edge right here, right, where it's the hump wave is on the axis. So you're 0 right there, which is here. So basically what you'll notice is that we can just stack this shape. Again, we can just stack this shape on top of this shape like this, but because we're taking away this part of this shape right here, right? We're taking that hump wave out of the square wave. We're destroying that part. We're subtracting it. So our resulting wave pulse looks like this. Boom. So it just looks like the hump part is taken out of the square, right? Where here in the middle we've got it's on the axis, right? It's a 0 point because that's when they're perfectly canceling each other out. The hump is 2 units tall and the square is 2 units tall. So right here we should have 0. And it literally just looks like we took that shape out, right? We destroyed that bit of shape, because that's what happens. So that's all for that one. I think that the shapes building off one another makes sense in terms of like if you just stack them, then you can kind of see what's going on here. You're just taking away this part from this part, like this drawing here I did, where I've got the shapes are stacked on top of each other and canceling out. I feel like is your go-to for how to figure these out, right? You just need to draw them on top of one another with the appropriate amounts. Like if you're adding them, they're adding, and if you're subtracting them, you're taking away that bit. And I think that's your best route of solving these problems. So if there's any questions, as usual, just let me know. Message me. If not, have a lovely day. If you've noticed that I didn't iron this one this time. I did steam it previously, but that seems like a lot of work, so I didn't do that. So let me know if I should iron them, I guess.